Hello everyone. This video covers section 6.1 of the book, which is systems of linear equations. And more specifically on 6.1, we're going to focus on Gaussian elimination. Gaussian elimination is something that you have done before in previous classes. Now we're just going to be a little more detailed about the process, but this is not completely new. Or at least it should not be completely new to anybody in the class. Now, in general, a system of equation looks like this. So this is the general format. You have you could technically have m equations and n variables, but in this section we're going to have the same number of equations as the same number of variables, so m is going to be equals to n. So that will create something that is called a square matrix, which again, this should not be a new concept. So the system of equation is usually written like this. Now the first thing to refresh your memory is that you can break it into technically three pieces. The matrix A, which again here we assume that m is equals to n, which it will make this a square matrix. So A is just the coefficients. Then you're going to need a new vector x, which is going to have a x1, x2, all the way to xn. So these are the three components of this system. So this is exactly the same thing as these three things. So you should know that these three things is exactly the same thing as this. Now, there is something called the augmented matrix. So augmented matrix, and the augmented matrix is technically just this matrix A, and you combine it with B, and you're gonna use this to do the Gaussian elimination process. So pretty much this is the notation for the augmented matrix, and all this means is that you still have the matrix A11, A12, A1n, A21, A22, and so forth. This will be A and N, and this will be A and 1. So like that is just A. So therefore, since you want the augmented matrix, you add, that's why this is called augmented, the second matrix. I mean, you augment to the matrix the part B, so then this will be B1, B2, B3, all the way to Bn. And this is typically gonna be called A with a tilde. That's how you are gonna know this is the augmented matrix. All right, so now that the notation is clear, what we're gonna focus on this section is on Gaussian elimination, which again, you have done this before, maybe not in the correct way, but you can do Gaussian elimination. Everybody has done this in basic algebra, and by basic algebra I mean college algebra from community college. Now for Gaussian elimination, remember that there is technically three operations. So you're going to have three operations that you can use to simplify the matrix. And the three operations are this. The first one is that you can multiply any equation. So now here, for example, this will be equation 1, this will be equation 2, equation 3, and so forth. So therefore, this will be like equation 1. Let me actually write here equation 1, equation 2, and so forth, all the way to equation n. The focus of this video and this section is Gaussian elimination. There are three main operations that you do in Gaussian elimination. And again, this is not new, this is something you've done before. Now we're just making it more detailed or official. So there is 3 operations that you use in Gaussian elimination. The first one is if lambda is a constant where it cannot be 0, then if you multiply any row, let's say EI, times the constant, then whatever you get, it can replace the original row. So that's the first operation. The second operation is a combination of the first one plus something else. And it says that if you multiply, let's say, the same row by a constant, and then you're gonna add it to a new row, and that's gonna replace the new row. Okay? And the last operation you can do is you can switch rows, and the notation is usually this: EI switches with EJ. So these are the 3 main operations, which again you have done this multiple times in basic algebra, not linear algebra, but basic algebra. So now we're gonna use this to see how Gaussian elimination works. Now, just to refresh your memory, the whole idea of Gaussian elimination is this: you're gonna use these operations to get a 0 here, and then you're gonna get a 0 here, and then a 0 here. So you do these operations until everything here becomes a 0, and then you do the same thing until all of this becomes a 0, and then all of this until you end up with 1. So technically in Gaussian elimination, the matrix gonna end up looking like this. You're gonna have A1, 1. You're still gonna, this is going to remain. All of this is going to be 0. You're still gonna have equations here. Okay, and then you're gonna use back substitution to solve the problem. Now notice that every time you do these operations, this is gonna change. So therefore this A11 is not gonna be the same thing as this A11, or this ANN is not gonna be the same one as this. So there must be a way to keep track of that, and I'll show you how to do that right now. But again, the idea is you get zeros here using this value. So you use this value to get zeros here. Then you use this one to get zeros here, and so forth. So let's do an example to see how this works. All right, so here I already have the augmented matrix, but the original problem is pretty much this. You have 3x1 plus 2x2 plus x3 is equals to 1. And then you have 3x2 plus 5x2 plus x3 is equals to 3. And then 2x1, this should be x1, plus 6x2 plus 7x3, this should equals to 1. So here clearly the matrix A is just 1, 2, 1. This is 2, 5, 1. This is 2, 6, 7. Here I copy a 3, should be just a 1. Here B is equals to 1, 3, 1. And therefore this is the augmented matrix right here. Augmented matrix. Right? So now to keep track of what step or what location are we at any given time, this one is going to be called the augmented matrix 1, which means this is the original problem. And remember, the goal is to get 0 here, here, and then here. here we have equation 1, equation 2, and equation 3. So you only have three equations. Now, the way that Gaussian elimination is going to work, Gaussian elimination, and this is the proper way, because remember when you took this class in college algebra or pre-calculus, as long as you get rid of these values, it doesn't matter how you do it. As long as you get rid of this and you solve for x1, x2, and x3, it's fine. Here, you had to follow the rules very precisely. You need to use this one to get zeros here and here. And once you're done with that, you're gonna use this one to get the zero here. Now remember that this one is technically A11, then this one is A12, and so forth. Okay. So the way in which we're gonna select what to do, this is a theoretical part. So we're gonna have EJ, so row EJ or equation EJ, then minus, you're gonna do AJI over A11, which you notice in this case, this is A11. Again, you have done this before. This is just the more formal way to do this. Okay, you should review what you know about this topic and put it in here. And then this will be E1, which is the first row. And whatever you get, you're gonna put it in row J or equation J, where here J is equals to 2, 3, 4, all the way to N, and clearly A11 cannot be equals to 0. Again, this is just a very fancy way to tell you need to get 0 here and then 0 here. Now this has a specific name. This is called the multiplier. And technically to find the multipliers, that means you're gonna use this row to get rid of all the zeros here and so forth. In our case, this is what we have. First, we leave the first row alone. So this is 1, 2, 1, 1, or the first equation alone. Then for the second equation, we're going to use E2 minus 3 over 1 E1. And whatever we get, we're going to put it in E2. Why? Because if you multiply this by minus 3 over 1, it will give you minus 3. Minus 3 plus 3 is 0. So that's why we're using that. So when we do that, the first value should become 0. And you should check this. This is very straightforward. This one should be minus 1, minus 2, and the last one is 0. Again, how do you get negative 1? Well, if you multiply this by minus 3, that will give you minus 6. Minus 6 plus 5 is negative 1. All right, so we follow the same rule. Then this will be E3 minus now 2 over 1 E1. Then put it in E3. Again, notice how we're using the E1, which is this one, to get rid of all of these values, and by that it means to get 0 here. So we do that, and this becomes 0, 2, this is positive 2, and then the last one is 5, and then for the augmented part, this will be negative 1. You should do this very carefully and check, because if you get one of them wrong, everything else is going to be wrong. Now, once we get rid of all the numbers here and we end up with zeros, which is what we have here, now this is going to be called the augmented matrix A, but now this will be the 2. So remember, the original one was 1. Once you get rid of this row, this is going to be 2. Once you get rid of this one, it's going to be 3, and so forth. All right, so the next step is to get rid of this 0 right here. All of this is now going to change. The only one that's going to change is now this row. So this usually takes longer just to write everything down. So this is what we have. Okay, 1, 0, -1, -2, 0. And now you want to get rid of this one right here. So you want to get a 0 there. So the operation is going to be E3. Remember, you need to use this one to get a 0 there. That's equation 2. So this is going to be minus, and then this is going to be 2 over -1 E2. And whatever you get, just put it in E3. Again, this -1 right here is nothing more than A22. All right, so this we already know is 0. This one should be 0, but you should check that that's the case. So if you multiply this by -2, you multiply this by -2, that will give you 2. If you divide by -1, it will be -2, and -2 plus 2 is 0. Then the next value, it should be 1. And then the last one is going to be -1. Why? If you multiply this by -2, it will give you 0, -1, you still have -1. And now this will be A tilde 3. Now from here, we get the following system. x1 plus 2x2 plus x3 is equals to 1. And then minus x2 minus 2x3 is equals to 0. And then 1 times x3 is equals to -1. Now, to solve the system, we're going to use back substitution. So back substitution is technically the second part of Gaussian elimination. And to complete the Gaussian elimination process, and back substitution tells you the following: xi, which is the answer, so this is what you want. So this is the answer to the problem. Xi is going to be ai n plus 1 minus the sum from j equals to I plus 1 to n, or aij xj, everything divided by aii, which, remember, these are the diagonal elements in the matrix. And this obviously is true for I equals to 1, 2, all the way to n. Remember that this is called reduce or triangular form. Clearly, it looks like a triangle. All right, let's look back to this problem and solve it using Gaussian elimination, using this formula. All right, let's write the system again we have, or the triangular system we ended with, which was this, minus x2 and x3 was equals to -1, or 1 times that. Now, since we're doing backward substitution, then the first thing we should do is solve for x3. So clearly x3 is equals to -1 divided by 1. Over here, this one is A34. Well, this one clearly is A33. And the answer to this is just equals to -1. Then x2 is going to be, once you get x3, you can plug it in here, and from here you can solve for x2. So x2 is going to be equals to 0 plus 2x 3 divided by -1, where remember that 0 is nothing more than 8 to 4, and x3, we already know what it is this value right here, but the number 2 is technically 8 to 3, and this one on the bottom is 8 to 2, and once you simplify everything, this is going to be 2 times -1 or -1, which is just equals to 2. Now finally, before I do the last part, remember that the formula was this: xi is equals to ai n plus 1 minus j equals to I plus 1 to n aij xj, everything divided by aii. Also notice that this is technically just bi. Remember, in the augmented matrix, the matrix A only goes to is n by n, so therefore this will be n by 1. So B will, instead of calling this like B1, this is the same thing as if this is A11, A12, it will be A1 n plus 1. So that's why you have the extra part here. So this is technically just row B, which are these values right here. This is the vector B. Right, so therefore for to find x3, sorry, not x3, x1, which is the last one, x1 is going to be equals to 1 minus 2x2 minus x3 divided by 1. And again, this is A14. This one, the 2 is A12. And the one in front here was A13. And this one is A11. So when you plug everything again, you can check that this is -2. The solution is x1 equals to -2, x2 is 2, and x3 is -1. And that's the answer. Now, let me just make a small note here. I'm sure that all of you could resolve this problem without going into these details, just by eliminating equation 1, equation 2, and you will get to the answer eventually. The reason why the process is important to see how this is supposed to be done properly is going to be for the theoretical purposes mostly. Because if I could ask you this question by itself, you could solve it easily just by technically trial and error and pick any combinations you want. You'll get there eventually, but what the purpose is not to solve it, which at the end it is, but to see how the process works, how you do Gaussian elimination. Now, since this is a numerical analysis class, we are concerned about the computation time that it will take to do this process. And if you think about it, there is only technically 3 things or 4 things you're going to do here: add, subtract, multiply, and divide. Now, for a computer, it usually takes a little longer to multiply and divide than to add and subtract. So the next thing we're going to do here, actually the last part we will do for this section, is to calculate the cost. And by cost, we mean here how many multiplications and divisions is going to cost to solve the problem. So by cost here we mean multiply and divide and add and subtract. Let's look first to the multiplication and divisions, like how long or how many of them are required. Remember that the system we're trying to solve looks like this. You have A11, A12, all the way to A1n, and then because of the augmented matrix, this is A1n plus 1, which remember I mentioned this a few minutes ago. This is just technically B1. And then you have here A21, A22. This will be A2n plus 1, all the way to AN n plus 1. Well, this one is A1n. Actually, this is keeps going, and this will be A n1, and this will be A n n. Again, it's very important that you remember how the process works. We're going to use this to get rid of all of this. Okay? And then this one to get rid of all of this, and so forth. So the first thing you need to worry about are the multipliers. Okay? So how many multipliers do we need? Remember, the multiplier was the number that when you combine these two, this will give you 0. And the multipliers was AJI over AII, where remember this is the diagonal, and this is true for I equals to 1, 2, all the way to n minus 1. Why? Because you're going to get zeros here, here, and so forth. You're going to keep going until you stop. The last one you're going to do this, it will be n minus 1. So therefore, the I only goes up to n minus 1. All right, so if you're sleeping, this is the best time to wake up, because if you miss this, you'll never get it. So here it is. So how many multipliers we actually need? So how many of these one you need? Well, it depends on the matrix. Therefore, 4 are, it depends where you are in the matrix. So for I equals to 1, 2, all the way to n minus 1, the number of multipliers we're going to need, so the number of multipliers is going to be n minus I. How? For example, if we are in this column, you're going to need n minus 1, okay? If you're in this one, you're going to need n minus 2. In this one, you're going to need n minus 3, n minus 4, and so forth. So therefore, you need n minus I multipliers, which will be the values to find this, and this one then book denotes this MJI. Now remember, once you find the multipliers, the next steps to get the zeros here, 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 and so forth, you need to do these row operations. Remember, this is the multiplier, AJI over AII, EI, and whatever you get, you're gonna put it in EI. Now remember that once you find a multiplier, you have to multiply. The multiplier will give you 0 here, which is the goal, but then you're gonna have to change all of this. So not just this one, you still have to multiply this, add it to this, add it to this, and so forth. So this one requires 1, 2, all the way to n plus 1. So again, it depends on which row you are. So in general, this one is going to require n minus I, because that's going to be the number of multipliers, and then it will be n minus I plus 1. The plus 1 is because of this extra column here. Again, this is the value, the number of operations for only one row, depending on which I you are looking at. If I is 1, so let's keep I equals to 1. So if I is 1, remember you're gonna need this multiplier and to get 0, and once you get 0 here, this value is gonna change 2. This is gonna change 2. You're multiplying this, so you're gonna need n minus 1. In this case, it will be n minus 1 plus 1. What will give you just n? Why? Because you're gonna need n multiplications in here. Notice how if it is n multiplications, that will be from here to here. You don't have to worry about this one because this one is gonna be equals to 0. That's the whole point of multiplying or getting the multiplier, so that this will be 0. But then you still have to perform n multiplications or n minus I plus 1. So if I is 1, the ones will cancel and you will have to do it n times. Now if you were now here where this was 0 and this was 0, then you have to do less multiplication. So that's where the n minus I comes in. Therefore, the total number of, this implies that the total number of multiplications and divisions, okay, to get a triangular system. Remember, this is not the whole problem, just a triangular system is going to be n minus I, okay, because that's how many, these are the multipliers you need, plus n minus I times n minus I plus 1, which are the operations required to change everything in here. And this is going to be true, as I mentioned before, for I equals to 1, 2, all the way to n minus 1. Now, if you combine this, if you factor the n minus 1, or n minus I, this will give you n minus I times n minus I plus 2. That's just factoring. So again, this is not the total. When I say total here, I mean the total for a specific value of I, not for the total. So we are not there yet, but we'll get there in a little bit. So here total represents for a specific value of I. So for example, if I is 1, then it will take all these many operations to do the multiplier here and then get these values change. Now, before we add all the values, recall, okay, that the sum from j equals to 1 to m of any constant is just a constant times m. That's one of the formulas from calculus 1. Also that the sum from j equals to 1 to m of j is equals to m plus 1 over 2. And finally that the sum from j equals to 1 to m of j squared is equals to m plus 1 to m plus 1 over 2. You use these formulas when you had to compute the Riemann integrals in calculus 1 in chapter 5. And we're gonna need these formulas right now to add all the values of I. Remember that in the last page, we already have this for the multiplications and divisions. This is what we got. The total for I equals to 1, 2, all the way to n minus 1 was the following. It was n minus I times n minus I plus 2. Okay. If you distribute this, this will give you n squared minus 2ni plus I squared plus 2n minus 2i. And notice that this, you can factor it as n minus I squared. And this one you can factor it like this. Now notice, and you should check that this is the case, okay? So you convince yourselves that the sum, let's say from I equals to 1 to n minus 1 or n minus I. For example, if I is 1, this will be n minus 1, then n minus 2, and so forth, all the way to 1. that this is the same thing as just the sum from I equals to 1 to n minus 1 of I. Okay, so this is just algebraic manipulations to make our life easier. So therefore from here we will have, and this is now the actual total, okay, multiplications and divisions. All you have to do is sum all of this from I equals to 1 to n minus 1. So therefore we have the total should be the sum from I equals to 1 to n minus 1 of n minus I squared plus 2, the sum from I equals to 1 to n minus 1 to n minus I. Now using this, we can simplify this to be equals to just the sum from I equals to 1 to n minus 1 of I squared plus 2, the sum from I equals to 1 to n minus 1 of I. And then if we use the formulas that we just discussed in the last page, this is equals to n minus 1 times n times 2n minus 1 plus 1 divided by 6. That was from the formula of I squared plus 2n minus 1 times n divided by 2. Here the 2's cancel. This on the numerator becomes n times n minus 1. It will be 2n minus 1 divided by 6 plus n minus 1 times n. And then if you do a little bit more of algebra, and you should check this, okay, this equals to 2nq plus 3n squared minus 5n divided by 6. Notice that the determinant term here is technically nq, so this is technically going to be proportional to nq. So what this means is that you need to solve a system of equation that has, let's say, 100 equations, well then the value for n is equals to 100. So therefore the number of operations, we haven't discussed the addition and subtraction yet, the number of operations, it will be 1/3 times 100q, which is around 10 to the 6, which is a million divided by 3. So that's just the number of multiplications that it will take to solve this. That's why you need a computer to do this. If you do this by hand, you will be there for a long time. Now, if you look back to what we did so far, all we'll figure out were the number of multiplications and divisions. For addition and subtractions, it's very similar. So for addition and subtraction, it's actually a little bit easier to count than the multiplication and division, because notice that the operator or the operations are technically done using this formula. Okay, so these are the main operations, the E, I, and then this replaces the original values there. Notice that this was the multiplier, which is a division, then it was a multiplication, and then you had to do a subtraction. So technically these are mostly subtractions, not addition, so you had to keep doing the subtraction every time. So for that, this is going to be very similar to the multiplication. It actually is slightly easier. This will require n minus I times n minus 1 plus I subtractions for I again equals to 1, 2, all the way to n minus 1. Now, if we do the same sums that we just did right now, so you had to add for I equals to 1 to n minus 1 of n minus I squared plus I equals to 1 to n minus 1 of n minus I. And once you simplify all of this, you'll end up with nq minus n over 3, which again is proportional to just nq over 3. So therefore, just to do the triangular form, which is this, where you have a11 here, which has changed through, actually a11 doesn't change, but everything else is changing here to a and n, which it has changed depending on how many steps you've done. Remember, all of these will be zeros. So to accomplish this, technically it will take, if you added 2, it will be n over q over 3, the multiplication and divisions, plus nq over 3, which will be the addition and subtractions, which is around 2nq over 3. Now, we haven't even tackled the backward substitution, which is the last part. So what about the backward substitution? Well, for the backward substitution, the equation looks like this. You have a11 x1 plus a12 x2 and so forth, all the way to a1 n equals to, I guess, b1. And then you have a triangular matrix here, and this will be a and n. This should be xn. This is xn equals to bn. Okay. So remember, to solve this one, all requires is a division, and then you have to divide and go backwards using the formula. Remember, the xi was equals to this formula, the ai n plus 1 minus the summation divided by the diagonals. So this, and you should check this, is the same process that I did with a lot of detail at the beginning. And you check all of this. For the backward substitution, the multiplication and division is going to require 1 plus the sum from I equals to 1 to n minus 1 of n minus I plus 1, which is n squared plus n over 2. The reason why you have a 1 here is that to solve this one, there is no multiplications, it's just one division. So that's where this number comes from. Okay, so this 1 is technically from here. It's only a division. And then the addition and subtraction you're going to need is going to be the sum from I equals to 1 to n minus 1, n minus I plus 1 plus 1. And this, again, once you simplify, is around n squared minus n over 2. Now, that means the power for this one, this is n squared to do the substitution, and to do the triangular form is nq. So this takes a lot more work than to do the backward substitution. So the backward substitution is actually a lot less costly. So therefore, if you combine the total of everything, so the total, once you combine the back substitution plus the triangular form, is going to be of order of nq. So this would be nq. Since this is not going to change the power of the previous ones. Now the actual total number at the end is this, the multiplication and divisions. Once you add the back substitution to the previous one, and again you should check this, the total is going to be nq over 3 plus n squared minus n over 3, like that's the actual total. And for the addition and subtraction, the actual total is going to be nq over 3 plus n squared over 2 minus 5n over 6. So you should check this. This is a very good candidate for the next test.